So imagine you're staring at, like, a massive wall of a million microscopic Chinese characters.
Oh, wow. Just a wall of text.
Yeah, exactly. There are no page breaks, no bold fonts, no chapter headings, just this endless, chaotic ocean of text.
That sounds like a total nightmare to read.
It really is. And the question for you, the listener, is this. How do you teach a completely blind, rigidly logical machine to find something like the preface or chapter 1 in all that chaos?
Right, because that is a monumental translation problem. And, I mean, we're not talking about translating the language itself.
No, no, no.
We're talking about translating human inconsistency into, a machine-readable structure.
Exactly.
We're basically taking the highly organic and, let's be honest, sometimes really messy way authors organize literature and forcing it into a strict mathematical framework.
And that framework is exactly why, when you download a massive web novel or like a classic text to your e-reader, a perfectly nested, clickable table of contents just instantly slides out from the side of your screen.
Which is something we completely take for granted.
Oh, 100%. It doesn't just happen by magic. It happens because some programmers spent hours teaching the machine how to essentially swim through that ocean of characters without drowning.
Right. And today we are doing a deep dive into exactly how that unseen digital janitorial work actually happens.
Yes, we are looking at a highly specific, really fascinating snippet of Haskell programming code.
Which uses a library called text.megaparsec, right?
Yeah, exactly. And it's designed specifically to parse the intricate structure of Chinese books.
So the primary mission of this source code we're looking at is identifying the core architecture of a text.
Right, like the bones of the book.
Exactly. It has to accurately tag volumes, chapters, and all the complex frontmatter and backmatter.
Which programmers collectively refer to as book matters.
Yeah, book matters. And accomplishing this requires a pretty fundamental shift in how we approach coding.
Well, to build that clickable e-reader menu you're used to, the program first has to identify the text's hierarchy.
Right, it needs to know what's the top level.
Exactly. So it labels the volume as level 1, which the code designates as t-header 1, and then the chapter is level 2, designated as t-header 2.
Okay, that makes logical sense. But to successfully tag those sections in Chinese, the parser has to scan the text for very specific linguistic signposts, doesn't it?
It does. For volumes, it looks for specific Chinese characters. In pinyin, they are pronounced huan or pian.
Okay, so it's hunting for those specific words.
Right. And for chapters, it's hunting for words pronounced like zhang, ji, or hui.
See, the thing is, a human reader processes those variations completely automatically.
Well, for sure. You just kind of know.
Yeah, you understand you are reading a new section regardless of whether the author used the word for chapter or like the word for episode.
Right, your brain just autocorrects it.
But a machine parser, which is operating purely at the byte level, possesses absolutely zero intuition.
None at all.
So it will completely ignore a chapter if it is explicitly told to look for the word zhang, but the author decided to use jai instead.
That actually reminds me of trying to organize this massive, terribly edited fantasy series on my own digital bookshelf.
Oh no, let me guess. The naming conventions were a mess.
A complete disaster. Book 1 is literally called Book 1. But then Book 2 is suddenly a tome.
Of course it is.
Right? And the prequel is a part. And the individual chapters inside the books constantly switch from episodes to stanzas.
Stanzas, really?
I know. And as a human reader, I just roll with it. I understand the author's intent.
But your e-reader's software attempting to automatically index that.
It just crashes and burns.
Yeah.
It absolutely needs a dictionary of every possible synonym to figure it out.
And that's exactly the problem here. The initial version of the Haskell code we're analyzing handled that exact problem with pure brute force.
Brute force? How so?
Well, it relied on hard-coded string commands. The developer literally typed out separate instructions for every single word.
Wait, like step-by-step instructions?
Yeah, like look for the exact string for Juan, and if that fails, move to the next instruction and look for the exact string for Payin.
Okay, so, the code still worked, right?
Yeah.
It generated the table of contents.
Functionally, yes, the program executed. But structurally, it was incredibly brittle.
Brittle. That's a great word for it.
Yeah, and in large-scale software development, brittle code is a massive liability.
Because things change, right?
Exactly. If you are running thousands of books through this parser, and you suddenly encounter a text that uses a slightly archaic or uncommon term for a volume, the parser just fails.
Oh, And then what happens?
Well, a developer literally has to open up the core logic of the program, locate the specific parsing block for volumes, manually staple on another hard-coded string command for that new word, and recompile the whole thing.
Wow. So it's essentially unsustainable manual labor disguised as software engineering.
Exactly. Which brings us to the refactor.
Right. Okay, so hold on, because I'm looking at this refactored source code, and I don't quite get the hype around the solution here,
Okay, let's unpack it.
because the original code used a command that read choice, and then it had a list with string one and string pin. To me, as a non-programmer,
Yeah.
that makes total sense.
It's very readable, sure.
Just a readable list of choices. But the updated code replaces that by creating a brand new custom helper function. And now it just reads one of strings,
Right.
followed by the words Juan and Pin.
Right.
So why spend the time writing a completely new function just to delete the word string?
Mm.
Isn't that just like moving the furniture around on the screen?
It looks like that on the surface, yeah. But the genius of that change lies entirely in the abstraction.
Abstraction, how so?
Well, stripping out the word string seems trivial when you're just dealing with two characters, but underneath, the programmer fundamentally changed the nature of the machine's job.
Okay, I'm listening.
They shifted the burden of repetitive labor away from the human developer and onto the parser itself.
Oh, interesting. So the machine does the heavy lifting now.
Exactly. The new custom function, oneOfStrings, is defined by a highly elegant single-line mechanism. It's just choice.mapString.
Okay, walk me through that mechanism. How does choice.mapString actually change the game?
The map function is the real engine here. When you feed it a raw list of text, like our Chinese words for volume, it automatically applies the string parsing rule to every single item on that list simultaneously.
Okay, wait, let me try an analogy. Imagine you have a large basket of raw potatoes.
Okay, I like potatoes.
And those raw potatoes are our Chinese characters. The map function is essentially a conveyor belt that pushes every single potato through an automated slicer.
Yes.
So you don't have to stand there and slice them one by one, meaning the programmer doesn't have to manually type the word string before every single character. You just turn on the conveyor belt.
That is a completely perfect visualization. The code transforms a static list of raw data into a dynamic list of active parsers on the fly.
Oh, wow. That's really clever.
Yeah, and then the choice command just takes over. It looks at the actual book text to see if any of those newly minted parsers find a match.
So the programmer has essentially stopped writing individual rigid instructions.
Right.
And instead they've built a miniature factory that manufactures its own instruction.
Exactly. You've nailed it.
I see. So if our messy fantasy author from earlier decides to introduce a brand new structural term midway through book 5, like chronicle, I don't touch the complex logic of the factory.
Nope, not at all.
I just drop the raw word chronicle onto the conveyor belt, just into the raw text list, and the machine automatically maps the logic over it.
Because you are now managing data, not logic.
Managing data, not logic. That makes a lot of sense.
It's the absolute essence of the DRY principle in software.
TRY. Don't repeat yourself.
Yes, don't repeat yourself. And this philosophy cascaded through the rest of the code base. The programmer immediately leveraged this abstraction concept to create another, even more powerful helper function.
Is that the p-numbered function?
That's the one.
Yeah, I noticed that in the source. The old code had these massive, entirely separate blocks of logic, like one huge chunk for parsing a volume and another entirely different chunk for parsing a chapter.
Right, which is completely redundant because a volume and a chapter share the exact same underlying architectural DNA.
Oh, sure. You typically have a starting indicator, a number, a unit character, maybe a colon, and the title.
Exactly. The old brute force method needlessly duplicated all of that sequential logic. The new p-numbered function creates a universal template for that sequence.
So instead of writing the whole sequence twice, just call p-numbered.
Yes.
You just tell it, hey, this is a level 1 header, and you hand it the basket of volume characters.
Right. And for a chapter.
For a chapter, you just call the exact same p-numbered function, tell it this is a level 2 header, and hand it the basket of chapter characters. You have completely eliminated the duplicated code.
You've got it. But building this factory wasn't just an academic exercise in writing clean code. No, the p-numbered function was essentially just a warm-up. The true test of this abstraction engine, the real reason the programmer absolutely had to build the oneOfStrings helper, arrives when the parser hits the book matters.
Ah, the front matter and the back matter.
Exactly.
And this is where the sheer volume of structural variation would have made the old brute force method completely impossible to maintain.
Oh, it would have been a disaster.
Because a book doesn't just have a simple preface, right? It might have a foreword, an author's preface, a prologue, a synopsis, or an introduction.
The variations are practically endless.
I'm looking at the list of variations the code has to process in English translation. There are at least half a dozen distinct Chinese terms just for the front of the book alone.
And the backmatter is equally expansive. You have afterwords, postscripts, epilogues, appendices, acknowledgments, and indexes.
It's a lot to parse.
We are talking about a massive array of potential linguistic signposts. If a developer had to manually construct the logic for every single one of those terms.
Just typing string over and over.
Yeah, typing string over and over and nesting them in explicit choice commands. The code would become this sprawling, unreadable mess.
It would be an absolute nightmare to debug. I mean, when you are copy-pasting the same logical command 12 times in a row, you are eventually going to make a typo.
Oh, inevitably. And a missed comma or an unclosed bracket in a hard-coded list breaks the entire parser.
The whole thing just stops.
Right. But with the new factory approach, the developer simply drops all 12 of those raw terms into a single, clean text list.
They just feed that list to oneOfStrings.
Exactly. And the conveyor belt handles it instantly. The machine maps the parsing logic over the massive array without breaking a sweat.
So it's robust, scalable, and completely resistant to those repetitive human errors.
Precisely. The macro structure is basically solved at that point.
But parsing human text always forces you to confront the microscopic details.
Oh, always. The devil is in the details.
Because once you build a factory that perfectly identifies the chapter, you still have to teach the machine how to read the punctuation, separating the chapter number from the chapter title.
Ah, yes, the piece separator function. This is where we see the intense friction between human typography and rigid machine logic.
Honestly, this part of the source code blew my mind.
Really? Why is that?
Because it focuses on something you and I would never even register while reading. We are talking about colons.
Just simple colons.
Right. To us, reading on a screen, a colon is just a colon. It just signals a pause before a title. We don't examine it.
We just read right past it.
Exactly. But to this Haskell parser, a full-width Chinese colon, which, takes up a full square block of space to match the surrounding Chinese characters, is a completely different universe than a standard Western half-width colon.
They are completely unrelated to the machine. At the raw byte encoding level, those two colons share absolutely zero relation to each other.
That's so wild to think about.
They don't share the same hexadecimal value. So a brittle parser that is looking strictly for a standard Western colon will hit a full-width Chinese colon and just fail to recognize it as a separator.
It'll just assume it's part of the text, right?
Exactly. It will then merge the chapter number directly into the title, corrupting the entire digital table of contents.
And it gets even messier, because human beings are incredibly inconsistent typists.
Oh, human error is the biggest variable.
Right. Like, sometimes the person digitizing the text didn't use a colon at all. They just mashed the spacebar a couple of times between the number and the title.
Which happens all the time. The piece separator function navigates this typographic minefield using the choice mechanic we discussed earlier.
So it's doing multiple checks.
Yeah. It explicitly checks the byte encoding for a full-width colon. If it doesn't find one, it checks for a half-width colon. And if that fails, it relies on a command called hspace1.
hspace1, meaning it accounts for any arbitrary string of horizontal blank spaces.
Right. You got it. 1 space, 5 spaces, a massive tab indent. The machine catches it all.
So it basically creates a flexible boundary.
Yes. The rule essentially dictates, look for the full-width colon, the half-width colon, or a bunch of empty space.
And if you find any of those three things, treat it as the official wall separating the chapter number from the chapter title.
Exactly. And this is exactly why this invisible digital janitorial work matters so much.
So the next time you are frustrated because a downloaded document's formatting is slightly off, think about the sheer amount of typographic chaos the machine is attempting to navigate behind the scenes.
It's staggering. The programmer literally has to anticipate that the original author might have accidentally left their keyboard input set to English while typing a Chinese document.
Which results in a tiny half-width colon right in the middle of a massive full-width text block.
Right. Ultimately, this snippet of Haskell code serves as a masterclass in defensive architecture.
Defensive architecture, I like that phrase.
Because by applying functional programming principles, the developer built a parser that does not just react rigidly to a pristine theoretical text.
It adapts fluidly to the inherent, unavoidable messiness of human typing.
Exactly. They took a chaotic ocean of characters, completely abandoned the brittle approach of hard-coding every possible variation and instead built an elegant factory.
Functions like oneOfStrings and p-numbered just abstract the complex logic away.
They turn an impossible translation task into a smooth, automated pipeline.
It shifts the dynamic entirely. The code manages the strict structural rules, and the human programmer only needs to manage the vocabulary list.
It is a brilliant separation of concerns.
It really is. Which leaves me with the final thought for you to mull over as we wrap up this deep dive.
Well, let's hear it.
Well, we tend to look at software development as a deeply technical, highly mathematical discipline.
Sure, it usually is.
But to build a resilient system like this, to account for every bizarre synonym for prologue, and to anticipate the minute byte encoding difference between a full-width and half-width colon, you cannot just know the machine.
That's a great point. You have to know the people writing the text.
Right. If human language is this full of endless variations and unpredictable typographic quirks, are programmers ultimately just writing code?
Or are they doing something more?
Exactly. Or, to get a machine to truly read a book, are they forced to become digital linguists, spending their time decoding the messy, unpredictable humans who wrote the text in the first place?
That is a fascinating way to look at it.
Think about that the next time you tap a perfectly formatted table of contents on your screen.